Okay. BigM method is we used BigM method if the constraint contains at least one slack variable and not slack variable, surplus variable. Okay. Uh, if constraint does not have slack variable, then we add an artificial variable to initial basic variable, and we assign the cost of that artificial variable as minus m, where m is a very huge positive quantity, and uh, then another important thing is once an artificial variable leaves the basis, then we don't need to include artificial variable in further computation and solve the modified problem by applying the simplex method. Okay, so BigM method is used when at least one constraint in the standard form of LPP does not have a slack variable. Okay, that means if it involves a surplus variable or artificial variable. So these are the conclusions. If all the artificial variables are in 0 in the optimal solution of modified LPP, then we obtain the optimal solution to the original LPP. Okay, modified LPP means LPP involving slack and not slack. Modified LPP means the LPP involved our slack, surplus, and artificial variables. Okay, that means standard LPP. Okay, in our standard LPP attains the optimum value, and if all the artificial variables are in 0 level, and all the artificial variables are in 0 level, then that is the optimal solution to original LPP, that is given LPP. Okay. Then another condition is if the final simplex table contains a non-zero artificial variable, then LPP has no feasible solution. That means we reach the optimal solution of the modified LPP, but there is an artificial variable in the basis with a non-zero level. Okay, then that means presently artificial variable is basic with a non-zero level. Then the original LPP has no feasible solution, and also we have two more conditions. Suppose the modified LPP is unbounded. Modified LPP unbounded means we have an entering variable, but there is no living variable. That is the situation. Okay, suppose we have an entering variable, but there is no living variable. There is no living variable means all the entry in the respective column are negative. If all the entry in the respective column is less than or equal to 0, then we can take the ratio. Okay, so that means there is no living variable. That is a condition for unbounded solution. Okay, suppose the modified LPP is unbounded, then we have two conclusions about original LPP. The original LPP has no feasible solution, or original LPP is unbounded if it has a feasible solution. Okay, if original LPP has a feasible solution, then it is unbounded. Feasible solution means suppose in this table all the artificial variables are 0 level, then it has a feasible solution. In that case, original LPP is unbounded. Otherwise, original LPP is not feasible. Okay, anyway, if the modified LPP is unbounded, we have no optimal solution. With either original LPP has no feasible solution, or original LPP is unbounded. Anyway, we have no optimal solution. Okay, so let's see an example. Minimize z is equal to minus 3x1 minus 2x2 minus x3 subject to the constraints. Okay, and what about this x3? Here x3, the coefficient of x3 is 1, and there is no term containing x3 in the second constraint. That means we can treat x3 as a basic. Okay, we can treat x3 as a slack variable, because it's when we write the table, initial simplex table, then corresponding to x3 we get a column like this 1 0, isn't it? So it is like a slack variable as well. So we no need to introduce extra slack variable. Okay, so we can, in this case, we can treat this x3 as a slack variable. And what about the second constraint? In the second constraint, there is no slack variable because it is 3x1 plus 4x2 equal to 11. There is no variable like 0 1. Okay, so we have to introduce an extra variable, but this is already an equation, so we can't introduce slack or surplus variable. So here we introduce an artificial variable, that is a1. Okay, and also this is a minimization problem, so we have to convert this as a maximization problem. So this problem becomes maximize some z star equal to minus times this one, that is 3x1 plus 2x2 plus x3. And what about our constraints? The first constraint is, there is no change in the first constraint, it is 2x1 plus 5x2 plus x3 equal to 12. There is no change because we can treat x3 as a x3 has a almost slack variable. It is like a 1-0 form. Okay. And what about the second constraint? The second constraint, there is no slack variable, or there is no variable like slack variable. So we have to introduce an artificial variable because already this is an equation, not an equation. Okay, so that become 3x1 plus 4x2 plus some a1 equal to 11. Okay, then what is the cost of artificial variable in objective function? This is our new objective function. So the cost of artificial variable in the objective function is minus m, a huge quantity. M is very huge positive quantity. So minus m a1. Okay, now this is the new objective function, 3x1 plus 2x2 plus x3 minus m a1. Okay, subject to these two constraints. Again, we have a problem. X1 is unrestricted in sign, so we have to convert x1 as a we have to convert x1 as a difference of two non-zero as non-zero. We have to convert x1 as a difference of two non-negative variables. Okay, so that is the next procedure. So LPP become like this. So LPP become maximum z star equal to 3x1 plus minus ma1 subject to these two constraints. There is no change in the first constraint because x3 play the role of slack variable, isn't it? Because the coefficient of x3 in our table is 1-0. That's why here x3 play a role of slack variable. And in the second constraint, a1 play the role of slack variable because the coefficient of a1 in the initial simplex table is 0, 1 because there is no a1 in the first constraint. Okay. Okay, next we have to replace this unrestricted variable using x1 dash. So we are going to replace x1 by x1 dash minus x1 double dash, isn't it? And here x1 and x1 dash both are non-negative. This is possible. Every real number can be written as difference of two positive numbers. This is possible. Okay, so what about the final table, final standard form? So this is the standard form of given LPP. Maximum z star equal to like this. We replace all the x1. We replace all the x1s by x1 dash comma x1 dash minus x1 double dash. That's why this becomes 3x1 dash minus 3x1 double dash plus etc. And this constraint becomes 2x1 dash minus 2x1 double dash plus etc etc etc. Okay, so this is the standard form of given LPP. We have to optimize this LPP. This is called our modified LPP. This is not given LPP. Okay, this is called modified LPP. This is the given LPP. This is given LPP. This is our original LPP. Okay, in our technical term, this is our original LPP. And this is the modified LPP. We are going to optimize this modified LPP using simplex method. Okay, we are going to optimize this modified LPP using simplex method. Depending on the nature of this modified LPP, we can conclude about original LPP. Okay, that is the that is these conclusions. Okay, depending on the nature of the modified LPP, we can conclude about original LPP. Okay, for example, if all the artificial variables are 0 in the optimum solution of modified LPP, then we obtain optimal solution to the original LPP. Okay, similarly we have different observations are there. Okay, so this is the LPP, modified LPP. Next we have to write the first initial simplex table of this modified LPP. We know how to write the initial simplex table. Now we have 1, 2, 3, 4, 5 variables are there. Okay, we have 5 variables. So this is the initial simplex table. 3 minus 3, 2, 1 minus m. They are the cost. And initially in this example, what are the basic variable? In this example, what are the basic variables? Initially, what are the basic variables? x3 and a1 are the basic variable because they play the role of slack variable like in our ordinary LPP. Okay, so we set all other variables are non-basic. They are basic, and x1 dash, x1 double dash, x2 all are non-basic. So that means they are 0. So they are 0 means x3 equal to 12, a1 equal to 11. Okay, then everything is similar to our simplex method. So that's why the initial simplex table involves two variables. One is x3, other is a1, and coefficient of x3 is 1, and coefficient of a1 is minus m, where m is a very huge positive quantity. By solving that two equations, we get x3 is 12 and a1 is 11, and they are the coefficients. Okay, then you can evaluate zj's. What about zj? What about z1? What is z1? What is z1? How to find z1? Cost into respective column. Yeah, cost into respective column. So in the case of first one, it is 1 into 2 plus minus m into 3. So minus 3m plus 2. You got it? So similarly, you can evaluate all the CJs. Okay. So the first one is minus 3m plus 2. Then similarly, we can evaluate all the coefficients. In the second case, it is minus 2 plus 3m. That is 3m minus 2. Okay. So this is minus 4m plus 5, 1 minus m. Is it okay? Then what is our next procedure? Cj minus Zj. Cj's are there. So we have to find the difference between C1 minus Z1, C2 minus Z2, C3 minus Z3, like that. So this become 3m plus 1. 3 minus this quantity, that is 3m plus 1. Minus 3 minus this quantity is minus 3m minus 1, etc. Then what is our next procedure? Next we have to identify it is optimum or not. Is it an optimum? Is it an optimum table? No, because not all of them are less than or equal to 0. If all of them are less than or equal to 0, then we reach optimum. This is not the case. So we have to choose the maximum. Okay, which is the maximum? We assume that m is a large quantity, large positive quantity. Yes. Yes. So 4m minus 3 is the maximum. Okay, because we assume that m is a large quantity. So we choose x2 as entering variable. Okay, next we have to find the ratio corresponding to positive entries. Okay, here both are positive, so we can take the ratio, that is 12 by 5 and 11 by 4. 12 by 5 and 11 by 4. Then which one is a living variable? Which one is living variable? Yeah, x3 is a living variable. We take the minimum. Okay, out of these two we have to take the minimum. So minimum is 12 by 5, so that is corresponding to x3. So the living variable is x3. So as similar to our LPP, this is the pivot element. Okay, next we have to make this 5 as 1 and 4 as 0 using elementary row operations. So first of all, we divide with the 5. And okay, what is the change? The change in this side, x3 will leaves the basis. X3 will leaves the basis. X2 will enter the basis. That is a change. Okay, so x2 will enter the basis. So x2, and what is the cost? Cost is 2. That is a difference. Okay, so x2 is enter the basis and its corresponding cost is 2, and we divide 5 with all other elements. So this becomes 12 by 5, 2 by 5, etc. Okay, then next one we have to make this 4 as 0 using elementary operation. So if you take this row as R2 and this as R1, then how to make this 4 as 0? R2 goes to R2 minus 4R1. Okay, if you take this as R2 and this as R1, then we can take then this 4 becomes 0 using this elementary row operations, R2 minus 4R1. Okay, so after this operation, this become like this, 7 by 5. There is no change in the cost and artificial variable because there is no change in this variable. Okay, And next we have to find zj's, as similar to the previous case. These are the zj's. And next we have to find cj minus zj. These are the cj minus zj. Is it an optimum? Yeah, not all of them are less than or equal to 0. There is one term which is positive, 7m by 5 plus 11 by 5. This is positive. Okay, all other are less than or equal to 0. So anyway, this one is our entering variable, x1 dash is entering, and you take the ratio and take the minimum, that gives the living variable. So in this case, these are the ratios, and a1 is a living variable. A1 is living variable. Okay, so next, in the next iteration we are going to replace this. So this is our pivot element. So in next iteration we are going to replace this a1 by x1 dash, and the corresponding cost become 3. Okay, that is a change. So this is x1 dash and cost is 3, and also we have to multiply this row with it 5 by 7 to make this entry as 1. Okay, we multiply with the 5 by 7. So these are the changes. No need to compute the column corresponding to artificial variable once they leave. Okay, now in this iteration, artificial variable leaves the basis, so no need to compute the column corresponding to the artificial variable. For further computation, we no need to compute column corresponding to artificial variable. That's why I just blank. That's why I put this as a blank. Okay. Then okay, next we have to convert this 2 by 5 as 0. What is the operation? You take okay, if you take this as some r1 and this is r2, then what is the change? R1 goes to r1. This is our r1, this is our r2. Then how to make this entry as 0? R1 goes to r1 minus this is our r1. This row, we take this row as r1, this row as r2. We have to convert this 2 by 5 as 0 using this 1. So what is the operation? R2. Yeah, that is 2 by 5 r2. Okay, so using this operation, this become r1 goes to r1 minus 2 by 5 r2. This entry becomes 0. Okay, so this is the corresponding change. Okay, again we have to calculate zj and zj and zj minus zj. Again there is a positive term 13 by 7, so that is our entering variable. You take the ratio, okay, here corresponding to this entering column there is only one positive term, this is negative, so no need to take the ratio corresponding to this negative entry. So we have only one ratio, that is 2 by 3 by 7. That's why this is 14 by 3. Okay, so there is the minimum, it's minimum, this is itself. So here the living variable is x2, entering variable is x3. Okay, so next iteration. So will x3 is in a basic variable, now x3 is basic and corresponding cost is 1, and make this as 1 by dividing by 3, not 3 here. Here this is the pivot element, so we multiply with the 7 by 3 to convert this as 1. Okay, so okay, anyway this term is 1, and next this becomes 0 using corresponding elementary row operation. No need to compute the column corresponding to the artificial variable. Okay, so these are the zj's, and this is our cj minus zj. Now all the cj minus zj's are less than or equal to 0. This is the indication that this modified LPP is in optimum table. The modified LPP is in optimum state. Okay, because all the zj minus zj are less than or equal to 0. Okay, then what is the condition that original LPP is in optimum state? What is the condition that original LPP is in optimum state? If all the Zj minus Zj's are less than or equal to 0 and all the artificial variables are in 0 level, that is the condition. I will show you. That is the condition for original LPP has optimum. See this. If all the artificial variables are in 0 level, in the optimum solution of modified LPP. Now we reach the optimum table of modified LPP. And what about the values of artificial variable in the optimum table? In this example, what is the value of artificial variable in optimum table? What is the value of artificial variable in this optimum table? Or what is the state of artificial variable? Yeah, now this artificial variable is non-basic because not in the basis. So its value is 0. All the non-basic variables are 0. So presently A1 is 0. So what is the conclusion? Here all the Zj minus Zj's are less than or equal to 0 and we have only one artificial variable which is in 0 level. So we reach the optimum solution of original LPP combining these two. All the Cj minus Zj's are less than or equal to 0 and all the artificial variables should in 0 level. That is the condition that original LPP is in optimum state. Okay, so now the original LPP is in optimum state, so we can easily find the solution. What is the value of the solution? What about x1 dash x sorry, this is what is the value of x1 dash, x1 double dash, x2 and x3? What are the values? What about x1 dash? 11 by 3. This one? 0, 0, 0, 14 by 3. Okay. So our decision variables are x1, x2 and x3. We can easily find x1. We know that x1 is equal to x1 dash minus x1 double dash. So that is 11 by 3 minus 0. So that is 11 by 3. Okay. So all the Cj minus Zj's are less than or equal to 0 and artificial variables are in 0 level. So optimal solution is reached. Optimal solution for original LPP is reached. Okay. So the optimal solution is 11 by 3, 0, 14 by 3. And we have to find, the minimum of Z. What is maximum of Z star? What is our Z star? Z star is nothing. Z star is equal to 3x1 plus 2x2. This is our Z star. Okay, so maximum of Z star by plugging the values of x1, x2, x3 in this equation, we get 47 by 3. We have to find the minimum of Z. What about the minimum of Z? It is a negative of this one. Okay, we know that minimum of Z is equal to minus maximum of minus Z. Z star means minus Z. Okay, so that is a relation. Minimum of Z is equal to minus maximum of minus Z. Minus Z is nothing, it is our Z star. Okay, so that's why we put a minus sign. So minimum of Z is equal to minus 47 by 3. Or you simply plug these values x1, x2, x3 in the original objective function. What is our original objective function? Original objective function Z is equal to minus 3x1 minus 2x2 minus x. This is our original objective function, minimize. Okay, the values of the variables are no change in values of the variable. So either you can find the value by putting a minus sign on this maximum Z star, or you can put these values in the original objective function to get the minimum value. Okay. The next example, maximize Z is equal to x1 plus x2 subject to the constraints x1 plus 3x2 less than or equal to 9 and this one. And what about its standard form? We know that in standard form right hand side should be positive. Okay, In standard form, right hand side should be positive. So the constraints are like this: x1 plus 3x2 plus s1, an artificial variable equal to 9, because this is a less than or equal to type. So we can introduce a slack variable. This is a slack variable. And what about the second constraint? This is not in standard form. So for standard form, we have to convert the right hand side is positive. So by multiplying a minus sign, this becomes minus x1 plus 4x2 greater than or equal to 16. So we have to introduce a surplus variable. This is greater than or equal to type. That's why we introduce a minus s2. Okay, to construct a basic solution, initial basic solution, we have to introduce an artificial variable. You got it? So it's a step-by-step procedure is like this: minus x1 plus 4x2 minus some s2 equal to 16. To make an equation, we introduce a surplus variable. Okay, then to get a initial basic solution, we have to introduce a positive variable like this. That's why this is minus x1 plus 4x2 minus s2 plus some a1 equal to 16. These type of variables are called artificial variables. Okay, its cost should be minus n. So that's why objective function is like this: maximize z is equal to x1 plus x2 plus 0 s1 plus 0. Cost of slack and surplus variables are always 0. 0 s1 plus 0 s2 minus a1. So this is the new objective function, and these are the variables. Now everything is ready. So this is our modified LPP. You got it? This is our modified LPP. Next, we have to solve this modified LPP using simplex method. Okay, so this is our initial simplex table. Here the our initial basic variables are s1 and a1. Okay, initial basic variables are s1 and a1. The coefficient of s1 is 0 and coefficient of a1 is minus m. Then they are the initial solutions of s1 and a1. Then you can write this initial table like this. Then what about z1? What about z1? What is the value of z1? M, that is m. So this is minus 4m, etc. like that. Then we consider Cj minus Zj. Okay, is it an optimum? Is it an optimum? No. These two are non. These two are less than or equal to 0. These two quantities are negative. This is less than or 0. Everything is except only one. This is a positive quantity. Okay, except this second quantity, all other are less than or equal to 0. Okay, so this is the entering variable. So next we have to find the ratios. So ratios are 3 and 4, which is choose the minimum. So this 3 is our pivot element. So s1 will leave the basis and x2 will enter the basis. So what is the change? So here it is x2 and its cost is 1. So this is 1. Okay, then we have to convert this 3 as 1 by dividing this row by 3. Okay, so this entry become 3 and etc. like that. So yes, these are the corresponding values: x2 3 1 by 3 1 etc. And we have to convert this term as 0. How? To take this as some r2 and this is our r1, then what is the role? We have to convert this term is 0. So r2 goes to r2 minus, what is the operation? We convert this 4 as 0 for r1. Okay, so this is better. So r2 goes to r2 minus 4r1. After this operation, these are the values: 4 7 by 3 etc. Then we have to find zj's, then cj minus zj's. Is it an optimum? Is it an optimum table? Yes, this is an optimum table for modified LPP, isn't it? This is an optimum table for modified LPP because all the zj minus zj's are less than or equal to 0. My question: so this is an optimum for modified LPP. Is it an optimum for original LPP? No, because it involves, yeah, it contains an artificial variable with the non-zero level. That is very important. Suppose instead of 4, this entry is 0. You simply assume that instead of 4, this is 0. Then there is no problem. Artificial variable is in the basis, it's okay, but its value is 0. Then this table is an optimum for original PP. But this is not the case. Here, the artificial variable in the basis and in non-zero level. Okay, so the optimum table contains an artificial variable with the non-zero entry, non-zero level. So this is not an optimum table for original LPP. Then what is the indication? Then what is the conclusion about this table for original LPP? What is the conclusion? Optimum table with the non-zero entry. Then what happened? We'll show you. Solution. Yes, no feasible solution. That's correct. Optimum table with the optimum table with the non-zero artificial variable means this is the condition. And in the final simplex table contains a non-zero artificial variable. The final simplex table means all the Cj minus Hj's are less than or equal to 0. That is the meaning. The final simplex table means optimum table of the modified LPP. That means all the Cj minus Hj's are less than or equal to 0. And it contains non-zero artificial variable. Then LPP means original LPP. LPP means original LPP. LPP has no feasible solution. That means constraints are inconsistent. We can't solve that constraint. That's the idea. Okay, constraints are inconsistent. Okay, this is the second case. We have one more condition. If original modified LPP is unbounded, then we have two conditions. Okay. Anyway, so this problem, yes. Here we reach the optimum table, but there is an artificial variable a1 in the basic, that is in non-zero level. Artificial variable in the basic with the non-zero level. So LPP has no feasible solution. Got it. You can also verify this problem using graphical method. Okay, try it. You just plot these constraints. You plot these constraints in a paper. Then you can observe that this problem is actually unbounded, no feasible solution. That means there is no common region in the first quadrant. First quadrant means x1 and x2 are positive. Maybe, so for example, if you draw, suppose one region is, suppose one straight line is like this, and suppose another straight line is like this. Then what happens? There is no common region in the positive first quadrant, x1 and x2. x1 and x2 should be positive, isn't it? So suppose one straight line is like the other straight line is like this. Okay, one region is in this side, other region is in the side. There is no common region in the first quadrant. That means the constraints are inconsistent. Okay, there is no feasible solution. So that's the idea. So you can verify using graphical method. And we have to discuss one more problem to understand the conclusions of BigM method. Maximize this subject to these two constraints. So what about the standard form? What is the standard form? What is the standard form of this equation? What about the constraints? What is the
minus 3x1 plus x2.
Yeah, minus 3x1 plus x2 plus slack variable equal to 9. What about the second one? Minus x1 plus 4x2.
Minus 1 multiply. Greater than.
No, already it is in standard form. RHS should be positive. RHS should be positive. In standard form, RHS should be positive. So what is the standard form of second constraint?
Plus 4x2 minus s2.
S2 Yeah, equal to 16 is okay, but we have to solve this problem using simplex method. To solve simplex using simplex method, we have two basic variable. Okay. Okay, in the first constraints, this we can treat S1 as a basic, but what about the second constraint? There is no basic variable, or there is no slack variable. So what will do? Yes, so we have to introduce an artificial variable for
ഫസ്റ്റ് കേസിൽ x2 നമ്മളത് പറയത്തില്ലായിരുന്നോ മറ്റേ സ്ലാക്ക് വേരിയബിളിന്റെ
അല്ല പറ്റത്തില്ല because x2 is involved in the second constraint. So the column corresponding to x2 is actually 1 4. If it is 0, if it is, suppose there is no term like this for x2, then it's okay, then x2 can take the role of slack variable. But there is another problem, actually this is an inequality, so we have to introduce a new variable to compensate this less than or equal to constraint. കാരണം ഇത് ലെസ് ദാൻ ഓർ ഈക്വൽ ടു ആയതുകൊണ്ട് എന്തായാലും നമുക്കിവിടെ ഇട്ടേ പറ്റത്തുള്ളൂ. ഓക്കെ, ബിക്കോസ് ഇൻ സ്റ്റാൻഡേർഡ് ഫോമിലെല്ലാം ഇക്വേഷൻസ് ആയിരിക്കണം. സോ എങ്ങനെ വന്നാലും വി ഹാവ് ടു ഇൻട്രൊഡ്യൂസ് ആൻ എക്സ്ട്രാ വേരിയബിൾ. ഓക്കെ, ഇൻ ദ പ്രീവിയസ് കേസ് ദാറ്റ് ഇസ് ആൻ ഇക്വേഷൻ ലൈക്ക് -3x1 plus x2 equal to 9, അങ്ങനെ ഒരു ഇക്വേഷൻ ആയിരുന്നു അവിടെ. ആൻഡ് ദർ ഇസ് നോ x2 ഇൻ ദ സെക്കൻഡ് കൺസ്ട്രെയിന്റ്. ദാറ്റ്സ് വൈ ഇൻ ദാറ്റ് കേസ് വി ട്രീറ്റ് x2 ആസ് എ സ്ലാക്ക് വേരിയബിൾ. ഇവിടെ എന്തായാലും നമുക്ക് S1 ഇട്ടേ പറ്റത്തുള്ളൂ ടു മേക്ക് ആൻ ഇക്വേഷൻ. Okay, anyway, in the second constraints, we introduce the slack variable to make an equation. But to start to start our simplex method, we need two slack variables. But there is no slack variable in the second constraint, so we have to introduce a artificial variable. That is the role of slack variable. Okay, so what is the standard form? So in standard form of the second constraint is -x1 plus 4x2 minus s2 plus a1 equal to 16. Okay, so what is the cost in the objective function? What is the new objective function? Z is equal to maximize. What is x1 plus x2? What is the cost of s1 and s2?
s1 plus 0
minus ma1. So this is the new objective function. Okay, so this is a new objective function. These are the standard constraints. Okay, all the variables are non-negative. So this is the standard form of given LPP. Maximum z is equal to x1 plus x2, 0 s1 plus 0 s2 minus ma1, subject to these two constraints. Okay. So initially, what are the basic variables? Initially, what are the basic variables? Initially, which variables are basic? S1? S2 is not basic. Yeah, S2 and A1, because we have only two equations, so we need only two basic variable. Okay, we have only two equations, so we need only two basic variable. This S2 is not a basic variable, that's why we introduce an extra variable, because the role of S2, the coefficient of S2 is like 0 minus 1. The coefficient of S2 in the initial simplex table is 0 minus 1. This is not possible. Okay, so that's why we introduce an extra variable a1. So initially this s1 and a1 are basic variables, because the coefficient of s1 in the initial simplex table is 1 0 and coefficient of a1 in this initial simplex table is 0 1. നിങ്ങൾ ഇത് ഇങ്ങനെ ആലോചിച്ചാലും മതി. Okay, then only its solution. Then what is the initial solution of s1 and a1? What is the initial value of s1 and a1? is initial value of S1. They are basic. They are basic. Yes, S1 is now S1 and yeah, S1 is 9. What about A1? 16, because now S1 and A1 are only these two variables are basic. All other variables are non-basic. That means non-basic means they are 0. Presently they are 0. So if you substituting these variables are 0, automatically S1 is 9 and A1 is 16. Okay. Anyway, this is the idea. So we can write the initial simplex table, and this is our initial simplex table. S1 and A1 are basic variables. They are the values of S1 and A1, and they are the cost. Then you can write this initial simplex table. Then Zj, Cj minus Zj's, 1 minus m, 1 minus 4m become 1 plus 4m, etc. This is not an optimum table. It contains a positive quantity. So this is our entering variable. Then you take the ratio, that is 9 and 4, 9 by 1 and 16 by 4. That is, then minimum is corresponding to A1. So this is our pivot element. So A1 will leaves the basis, X2 will enter the basis. X2 will enter the basis means this entry is X2 and corresponding cost is 1. Okay, we have to make this 4 as 0 by 4 as 1 by dividing this row with 4. So these are the corresponding changes, 1 and 0, like this. Okay, then first of all we convert this 4 as 1. Then using the 1 we can easily make this as 0, because already here also 1. So you simply take R1 minus R2. R1 minus R2 gives 0. Okay, and no need to compute the column corresponding to artificial variable, because artificial variable leaves the basis. Once it leaves the basis, then we no need to compute the column corresponding to artificial variable. Then Cj's are there. This is Cj minus Zj. Okay, then which one is living variable? Sorry, which one is entering variable? Which one is entering variable? Is it an optimum table? Yeah, x1 will enter the basis. Okay, because the maximum corresponding to 5 by 4. Maximum corresponding to 5 by 4. So this will enter the basis. Which one is living variable? Is it possible to take the ratio? Is it possible? Yeah, here all the entries in this column, all the entries in entering variable, all the entries in the column corresponding to entering variable is negative. So there is no ratio. That means there is no living variable. What is the indication? It indicates that there is an entering variable, but there is no living variable. What is the indication? This indicates what? Yeah, that is the condition for unboundedness. Correct. That is a condition for unbounded solution. That is from our simplex method. Okay. So now we reach the step 3. Suppose that modified LPP is unbounded. Unbounded means we have an entering variable, but there is no living variable, because all the entries in this column is less than or equal to 0. That means there is no living variable. That is the condition for unbounded solution. Okay, so now the present table is unbounded table. That means modified LPP is unbounded. Then we have two cases. Either original LPP has no feasible solution, or original LPP is unbounded if it has a feasible solution. Okay, that is depending on the nature of our original problem. So we can closely analyze that problem. Okay, here this is an unbounded table. That means original LPP, the modified LPP is unbounded, but there is no artificial variable in non-zero level. Okay, if some artificial variable in non-zero level, then the problem has no feasible solution. But here now artificial variable are in zero level. That means this problem has a feasible solution but unbounded. You got it? So this problem has a feasible solution because artificial variable in the zero level. So problem has a feasible solution. Okay, that is the indication that original LPP is unbounded. You got it? Suppose some artificial variable with the non-zero level in this table, then that means original LPP has no feasible solution. Okay, so in total we have 4 cases. We can conclude these 4 cases. Like you can also
Sir, class
okay. വൈൻഡ് അപ്പ് ചെയ്യാം. അറ്റൻഡൻസ് നോക്കിയാ എല്ലാവരും ഉണ്ടോ?